Alright, another example. Same type, but again, we're going to do, instead of long division, we're going to do synthetic division. So we have the same polynomial, 2x squared minus 4x plus 2. This time our 0 is 1. And let's see what we get this time. Procedurally, we bring down the 2 and we multiply. We add together and we multiply. We add together, we get 0. Okay, this is our remainder. In other words, 2x squared minus 4x plus 2, if we were to factor it, one of the factors is x minus 1. That's what factor theorem tells us. If we divide and get a remainder of 0, then this that we divided by is a factor. Okay, the other factor is this leftover piece, which would be representing 2x minus 2. Gives us a way to factor polynomials. Now let's just show again this way using the remainder theorem. So if we were to find f of 1, it's 2 times 1 squared minus 4 times 1 plus 2. That's 2 times 1 minus 4 plus 2. It's 2 minus 2, which is 0. So we can see, again, same thing as synthetic substitution, as just evaluating the function. Next thing we're going to talk about is called the rational zeros theorem, and it looks kind of like this. Let's suppose that we have a function f of x equal to this, a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub 2 x squared plus a sub 1 x to the first plus a sub 0. Okay, so it's just a polynomial function in standard form. Notice highest power here, take one away, continue on down to the lowest powered constant here. To use this rational zeros theorem, we need only look at two parts of this function. That would always be the highest powered term and the constant term. Okay, so let's define it this way. We're going to let P be all factors of a sub 0. We're going to let Q be all factors of a sub n. So we list out all the factors of this one, all the factors of this number right here, and then we can say that all, let's say, possible rational zeros will be all possible rational zeros will be of the form p divided by q. Okay? So if a function has rational zeros, rational numbers are fractions, right? Like 2/3, 1/2, 1/4, negative 5/8, and whole numbers, integers, 3, 4, negative 2, etc. If a function has these rational zeros, then we're guaranteed that they're going to be of this form right here. And these numbers p and q are found by using these numbers up here. So we're going to illustrate that with a couple of maybe like 2 or 3 example problems, how that works, how we're going to use this theorem to help us find zeros of functions. And I guess I should also state too, before we go on to some examples, I'm doing this whenever the easy way to find zeros, which is factoring, doesn't work. Okay? If you remember back to your 6.3 notes, near the end of that, I did an example and I said the easiest way to do it is just to factor, so let's factor it. This is kind of a strategy I'm going to use when factoring doesn't work. Okay? Alright, this next example is just an illustration of that rational zeros theorem, just so we can get a grip on that. It says to list all the possible rational zeros of the function. We aren't actually going to find them. We're just going to practice making the list. Okay? So the list is of the form, if you recall, p divided by q from the last slide. P are all the factors of 5. Factors are all the ways we multiply two numbers to get 5. Okay, and those numbers are only 1 and 5. Now I use plus or minus of each of them because to get negative 5 it could be positive times negative or negative times positive. So I got to have them both. And Q are all the factors of 4. How can we multiply to get 4? That's 1 times 4, 2 times 2. I'm going to put them in order. 1, 2, and 4. And again, plus and minus for the same reasons, because positive times positive is a positive 4. Negative times negative would also make a positive 4. So it's always just plus and minus of all of them. Okay, so now maybe I want to write out the full list. 1 divided by each of these. So 1 divided by 1, let's just point them out here. 1 divided by 1 is 1. 1 divided by 2 is 1/2. 1 divided by 4 is 1/4. 5 divided by 1, 5 divided by 2, and then 5 divided by 4. Okay. There's my list of possible zeros. There are 12 possible rational zeros. Okay, 12 because there are 6 numbers here, positive and negative of each of them. So I've got 12 possibilities. The next task would be to actually find which ones are really the zeros, okay, of the possibilities. Alright, let's walk through an entire problem kind of step by step. We're asked to find all the rational zeros. Okay, so the first thing I'm going to do is figure out what are the possible rational zeros. The possible rational zeros, okay, this is the p divided by q. I'm going to take the factors of 2 divided by factors of 3. And if we want to write out a fuller list, I would have 1 divided by 1 is 1. 1 divided by 3 is 1/3. 2 divided by 1, 2 divided by 3. Okay, there's my list of possible zeros. There are 8 of them. Okay, we know, okay, let's talk about something else that we know from the last lesson. We know that this function is not going to have more than 3 zeros. Okay? I've got 8 possibilities, and these are just the rational ones. There could be irrational zeros. Okay? We'll find out in the next section there could be complex or imaginary zeros. But this function, no matter how it zeros, what form they are, it's not going to have more than 3 total. And I've got 8 to choose from. So from here we've got 2 options. We could just go with blind guessing. Let's guess 1/3 is a 0, and then let's do synthetic division to see if it is. And if it's not, well, then we take 1/3 off the list and we try something else, but we're just kind of blind guessing. I don't like the blind guessing game, so what I'm going to do next is I'm going to graph the function. Okay? The graph of the function is going to help me narrow down my possibilities. Okay, so I'm going to type in this function. Oops, and you do the same. Okay, I can see it being drawn right there. I'm going to zoom in just a little bit. It's still drawing. There we go. I'm going to zoom box just just because I want to see just the piece of this where the zeros are. I don't want to see everything. Okay, so here's the graph. And so I look at that function, and let's look at our list of zeros. Do we have anything that looks like it's on the list? You know, this looks like it crosses at -2. It looks like it crosses at 1. Maybe this number here is, maybe it's -1/3. But it looks like we have some possibilities, okay? So I've graphed the function, and now instead of blind guessing, okay? Again, so the graph, it looks like -2, 1, maybe -1/3. And notice that all those numbers are on my list up here. Okay, so it looks like instead of blind guessing, it looks like I can just try these numbers instead of the guess. Okay, so that's exactly what I'm going to do. So let's take this. We've got 3 for x to the third, 4 for x squared, -5 for x, -2. I am looking for a 0. If I don't get a remainder of 0, I'm not interested in that number. I'm just going to throw it out and try something else. And since the graph looks like these numbers, let's try these numbers. Let's try -2. So procedurally, I bring down the 3 and I multiply. I add together and I multiply. I add together and I multiply, and sure enough, it works. Okay? So I know that -2 is a 0. Alright, so let's try the +1. I'm just going to use these numbers right here. I'm looking for a 0. I'm going to try +1. I bring down the 3, I multiply, I add together, and I multiply, and sure enough, that's a 0. And I'm going to try the -1/3. I bring down the 3, I multiply, and sure enough, that's a 0 too. So, have I found all the zeros? I have found that my zeros are x equals -2, x equals 1, x equals -1/3. I confirm them with synthetic division here. So the graph made it look like they were, and then I confirmed over here by showing remainders of 0 all the way down.